Welcome everyone to another seminar of Physics Latam. Today we are very happy to have Professor David Wallace giving a lecture on the quantum measurement problem. He is a philosopher of physics, originally trained as a physicist. He earned a PhD in physics from the University of Oxford before shifting his focus towards fundamental and conceptual questions in physics, ultimately leading him into philosophy. He is currently professor at the University of Pittsburgh. His research explored the philosophy of physics with particularly emphasis on the Everett interpretation of quantum mechanics, often known as the many worlds interpretation. His book, The Emergent Multiverse, provides a comprehensive defense and development of this interpretation. Beyond quantum theory, his interests extend to quantum field theory, statistical mechanics, general relativity, and the philosophical implications of symmetries, gauge theories, and also general philosophy. Please remember to raise your hand at any point if people in the audience has any questions, and I will leave you with David. Please go ahead.
Great, thank you very much, and it's great to be here. So I should say at the outset, the course is philosophy of quantum field theory. Most of what I'm going to be saying is going to be fairly neutral as to whether we're talking about non-relativistic quantum mechanics, quantum field theory, various kind of solid state models, any application of the quantum formalism you like, really. In fact, that's one of the background points here, which is that the conceptual questions in understanding quantum mechanics have to be answered at a level which is compatible not just with the sort of non-relativistic models where a lot of discussions of the foundations of quantum mechanics happen, but with quantum field theory, which, as everyone in this course realizes, is the workhorse of modern theoretical physics. What I'm going to do in these lectures is just give a sort of introduction to the quantum measurement problem from what I hope is a fairly physics-centric perspective. I want to try to keep away as much as possible from the sort of way philosophers will often talk about these issues, about like what's the deep meaning of what's going on in quantum mechanics, and ask a little more practically, how do we understand quantum mechanics? How do we use quantum mechanics in contexts where we're not simply doing some algorithmic calculation, but where we need to be somewhat more thoughtful about the kind of modeling situation we're dealing with. And in terms of structure, what I'm going to begin by doing is trying to get you to sort of unlearn a little bit of what you learned long ago in undergraduate quantum mechanics about the way we think about measurement in the quantum formalism, and then take that as a starting point to say, well, how can we think about measurement and more generally our understanding of quantum mechanics? And I'm going to go through a few options and show what we've learned in most of a century of thinking about this. And one of the background things I'd like people to come away from is that different ways of thinking about quantum mechanics end up not just being words. They end up making a difference to how we use the theory to model physical systems, how we decide to set up particular problems, and there's been a back and forth between thinking about the conceptual structure of quantum mechanics and thinking about various applications of quantum mechanics that are that continues to this day and has been pretty fruitful. I think the first question I've got here more or less is going to be, I'm going to say, well, listen to the lecture and then come back to me, because in a sense you're very much asking how to understand quantum mechanics and how to think about the conceptual structure of quantum mechanics, and that's exactly what we're going to talk about. So bear with me. Okay, so let's begin. Here's something you see in at least some textbooks on quantum mechanics. It depends where you read, but this is a classic way of thinking about quantum mechanics. On top of the sort of basic formalism of Hilbert spaces and self-adjoint operators, you get an interpretative rule, a rule for making sense of what the theory says, and two pieces of dynamics. And the interpretive rule often doesn't even have a name in the physics literature. Philosophers often call it the eigenstate-eigenvalue link. It's just the principle that says, if I've got some observable O, then the quantum system has a definite value of that observable, if and only if its quantum state is an eigenstate of O. If it is an eigenstate of O, what is that definite value? It's the eigenvalue. And then you have two alternative bits of dynamics available. Between measurements, you've got the dynamics we all know and love, the dynamics that gets realized in quantum field theory, often through the path integral, but in more elementary quantum mechanics through the Schrödinger equation. But in any case, it tells you unitarily how the quantum state evolves from one time to another. And then we have a separate rule that applies between measurement, a collapse of the wave function, a stochastic dynamics, probabilistic dynamics, whereby if what we're doing is measuring some observable O, then immediately after the measurement, the system will end up in an eigenstate of that observable. Which eigenstate? Well, take the mod squared amplitude of that eigenstate in a product with the system's quantum state, mod square it, that's the probability. So you have what von Neumann sometimes talks about as process one and process two, one form of dynamics for quantum mechanics that happens between measurements, one piece of quantum dynamics that happens at the point of measurement. And if you put those two together, those various pieces together, you get what people in foundations often call the Born rule, after Max Born first writing it down. In physics practice, we often just call it the probability rule, which is just the classic result that if I'm measuring O, then the probability of getting a given outcome is given by the mod squared inner product of that outcome's eigenstate with the quantum state. And of course, we have generalizations for continuous observations, for degenerate observations, but the core ideas are still there. Could start again. So as a practical matter, if you think about applications of quantum mechanics, 99% of the time, we're actually not using that apparatus of eigenvector, eigenvalue link, and wave function collapse. All we're using is the probability rule. We have an experiment we want to carry out. We have possible outcomes. We want to know how probable it is that each outcome occurs. So what's the point of the collapse rule in our physics? And actually what I want to persuade you of the next few minutes is there isn't really any point. It's not really something that does much work in the way we apply physics. But up front, there are two main reasons you see in textbook and other discussions as to why we say the wave function collapses when measurement happens. And I should say what I mean by two reasons is two practical reasons in the application of physics, putting aside for the moment what our kind of conceptual understanding of the physics is. The two practical reasons are, firstly, we use the collapse rule in preparing a state. So if you think about the sort of classic Stern-Gerlach setup, the normal way you might imagine that you prepare a beam of particles, all of which have spin up in, say, the z direction, is you take an oven that just produces a stream of particles all in some mixed state. You split the beam through a beam splitter, and you throw away, or for an inhomogeneous magnetic field, you throw away the spin down beam, you keep the spin up beam, and now that's your starting state, that's your prepared state. So one thing we use wave function collapse for is state preparation. The other, and this is the thing you see more often, is the idea that wave function collapse is necessary to understand repeated measurements. We want to preserve the idea, so you'll read, so Dirac said back in the day, preserve the idea that if we measure the same thing twice in a row, we get the same answer. And you can see how it looks like wave function collapse is going to be necessary to understand that. If the system is an equal superposition of spin up and spin down, the probability rule says if I measure it, I'll get spin up with 50%, spin down with 50%. But if I want to say that measuring it twice will give me either spin up twice or spin down twice, it looks like I better collapse the wave function in order to correlate the two measurement results. Neither of those is persuasive as reasons. And I'm going to mostly talk here about that second example, the case of repeated measurements. If you step back and think for a moment, and this is particularly salient in a high energy physics context, we mostly don't want our measurements to give the same results upon repetition, because generally speaking, our measurement disturbs the system in a pretty violent way. The classic way to do an experiment in physics, particularly in high energy physics, is to take the system you want to study and throw it very, very hard at some other system and look what comes out. This is not a process guaranteed to leave the system undisturbed. Even the normal way you do say a Stern-Gerlach measurement, we normally slam the particle we're detecting onto a screen somewhere and look for the scintillations. And that slamming process is not a process that that's going to generally leave the system undisturbed. So there's a sense in which we only actually want repeated measurements to give the same result if the measurement doesn't disturb the system. That's getting quite close to being tautologous. That starts sounding like the measurement should only give the same result if it's a repeatable measurement. But there's an important physics idea behind that, which we can see and get clear on if we start to look at the way the measurement process itself can be described in quantum mechanics. And this will be a general theme of these lectures, the need to actually look at the quantum mechanics of the measurement process itself. So here's a very sort of schematic setup of how you might, within quantum mechanics, model the process of measuring spin. So our measurement device has some state that you might call ready, and it also has some state which is like when it's sort of set up ready to carry out the measurement. And it has some state that you might call up, which is, the pointer is pointing to the spin up result, and some other result down, which is the pointer is pointing to the spin down result. The definition of a good measurement process of spin, and I'm taking the z direction as tacit here, the basic criterion for it to be a good measurement is if the system is in fact in spin up, the measurement device reports that it's in spin up, and if the particle spin is spin down, then the measurement device reports that it's spin down. In other words, what we really require for measurement is it's a correlation between the pre-measurement state of the system being measured and the post-measurement state of the system doing the measuring. What isn't required per se for a measurement is that the post-measurement state of the thing being measured has any particular correlation to the result of the measurement. It might be that the measurement is disturbing. It might be that the measurement disrupts the spin of the system. If you're measuring, say, the polarization of a photon, it's very likely that the measurement destroys the photon entirely. All that matters is that a trace of the pre-measurement particle is left in the post-measurement state of the thing doing the measuring. And of course, if that's true, linear quantum mechanics tells us that the quantum state of the system, if I start with alpha spin up plus beta spin down ready, I'll end up with a potentially entangled state, but anyway, a superposition of the up result and the down result. And now we can say that a measurement is non-disturbing if in fact it does leave the post-measurement spin of the particle undisturbed. In other words, it's non-disturbing if spin up ready evolves to spin up up, and spin down ready evolves to spin down down. Those are the measurements we call non-disturbing measurements or weak measurements. In many cases, they're extremely difficult to do, but those are the cases where we would expect that if we carry out the measurement, we'll get the same result twice. Now, how can we ensure that? Well, the collapse rule would ensure it, because the system would end up after the collapse in an eigenstate of spin, up or down as appropriate. But to see whether we need to do that or whether just modeling the measurement suffices, then we can consider, well, how about if I have two spin measurement devices and I sequentially apply them? So here's what happens there. If I just imagine I've got two copies of the system and I apply whatever my unitary process is that implements the measurement. I start with alpha spin up plus beta spin down and both of the devices in the ready state. After the first measurement interaction, I've got alpha spin up ready plus beta spin down down ready. So the first measurement device is correlated to the spin particle, and second measurement device is unchanged. And then after the second step, again, just turning the handle of unitary dynamics, I've got a superposition of alpha spin up, result up on first device, result up on second device, plus beta spin down, down on first device, down on second device. All of that's unitary. We haven't collapsed the wave function. But if you look at applying the Born rule there, what probability does the Born rule give for saying both measurement devices give result up, mod alpha squared? What probability does the Born rule give of saying both measurement results have spin down, mod beta squared? What probability does the Born rule give that the two measurement devices give different results? 0. So you can see that actually the unitary dynamics plus the Born rule, plus thinking a little bit about what physical process counts as a non-disturbing measurement, already suffices to recover the result that repeated measurements give the same answer. So that at least is not a reason to collapse the wave function. It's just a reason to do what people in quantum information call the church of the larger Hilbert space, to step outside and model the quantum mechanics of how our repeated measurement works. And we can say fairly similar things about the state preparation idea, although I'll leave that as an exercise to the reader. So why am I telling you all this? Well, I've wanted to make the case that if we want to understand measurement in quantum mechanics, we should put aside that it's part of the very formalism of quantum mechanics that we need to collapse the wave function. And in fact, we can go a bit further than that. If we look at a bit more carefully at how we use quantum mechanics, we can see that we better not collapse the wave function, because in various cases, it'll get us into trouble. And there's several examples we could give here, but I'll give two. The first is, what happens if we want to observe a quantum system continuously, constantly? The classic example of this is radioactive decay. If I have a radioisotope and it's decaying and I have a Geiger counter next to it, the Geiger counter is not observing the system at discrete moments in time. It's not like the Geiger counter switches on every millisecond and switches off again and is just briefly pulsing. The Geiger counter is constantly present. It's constantly set up so that if it encounters a decay product, it clicks. If it doesn't encounter a decay product, it doesn't click. And the quantum process of radioactive decay is likewise a smooth, continuous process. Modeling that quantum mechanically is not terribly difficult. Schematically, as you, I'm sure, all know from being immersed in quantum field theory at the moment, I get this kind of quantum state. I get an exponentially decaying undecayed state, and then I get a whole bunch of different decay products, time indexed, corresponding to different times at which the process, the radioisotope might have decayed. That's perfectly well defined. If I were to try to apply the Born rule to that process, it gives a perfectly straightforward and correct prediction. It tells me that the probability that the system is undecayed at a given time is modulus e to the minus t over 2 tau squared, i.e. e to the minus t over tau, i.e. exponential decay, just as we expect. If you try collapsing the wave function, you start getting into trouble, because the obvious question is, when should you collapse it? How often should you collapse it? If the Geiger counter operated in discrete clicks, if it just turned on once a second, the answer presumably would be that once a second you should collapse the wave function. And then once a second, the wave function would either collapse to undecayed or to some decay product. And you can do that, and that's fine. But Geiger counters don't work that way. Geiger counters are continually observing. One very natural thing you might think of is, okay, fine, let's take limits. Let's say that continuous observation is the limit of discrete observation in the limit as the time interval between observations goes to 0. It's been known for a long time, this is called the quantum Zeno effect, that if you model continuous measurement that way, you get paradox. The actual result is that the system doesn't decay at all. The result of continuously measuring a system that way is that the system is permanently frozen in its initial state. And it's not difficult to get an intuition for that. If you imagine I've got unitary evolution, the system is evolving out of some subspace that corresponds to its initial state. Sorry, it's whatever initial property it has. Every time I measure the system, I either project, and if I apply a collapse, I either project it back into that space or project it to something orthogonal to that space. If you just take the limit of what unitary evolution looks like at short times, you'll find that the for sufficiently rapid observation, then the collapsing back to where it started process dominates, and the system just never gets out of its initial subspace. So whatever continuous observation should be, it can't be that. And Misra and Sudarshan in the 70s, when they proved the quantum Zeno effect, did think that collapse needed to be part of the formalism of quantum mechanics. And they thought this was a paradox. They thought that if that's how things go, then we just don't have any good theory of continuous observation. But in fact, the paradox was resolved quite satisfactorily a few years later. If one simply models the unitary process by which the Geiger counter responds, then there's a response timescale that the Geiger counter has. If the Geiger counter's response timescale was short compared to the timescale on which the radioactive decay process happens, then indeed the system would be frozen by the Zeno effect. But in fact, the response time of Geiger counters to radioisotopes is very, very long compared to the timescale on which the radioisotope decay process happens. So you can quantify the system, you can model it perfectly well, you can predict that continuous observation works fine. So take home from that, the Born rule works perfectly fine for radioactive decay. The collapse rule gets you into trouble. It's not clear how you'd apply it, and if you do apply it in one of the natural ways of making sense of it, you just freeze the system rigid. So continuous observation is one reason why the collapse rule can't be a general part of the formalism of quantum mechanics. The other, or another reason, is one that's close to the topic of this lecture course, which is how you should think about relativistic measurements. If you collapse the wave function, we know from entanglement, from Bell-type results, that this has implications for measurements made at space-like separated distances. So if I make a measurement on one side of the lab of an entangled system where the other half of the system's on the other side of the lab, that has to show up in statistics of measurements made on the other side of the lab. You can't signal that way, but you have to have those correlations. You can see from that, if you actually collapse the wave function, the collapse would have to be instantaneous. What does instantaneous even mean in a relativistic theory? Seems to involve some sort of choice of preferred reference frame. Even specifying that mathematically is going to be pretty difficult. We don't, however, have any problem in practice applying quantum mechanics to relativistic systems. In fact, this isn't even a problem you'll meet if you do a relativistic quantum field theory course. Why don't you meet it? Because you're never actually using the collapse rule in applying relativistic quantum mechanics. You're just using the probability rule, usually applied to the momentum basis. So if you think about the classic prediction in particle physics is normally a scattering cross-section. What's a scattering cross-section? It's basically downstream of a transition amplitude between states in the momentum basis. So again, we use the Born probability rule. We don't use the collapse rule. So take home from all of that. The basic starting point of quantum mechanics is unitary dynamics plus the probability rule. So then what is this supposed problem of measurement that physicists and philosophers have been worried about for 100 years? Well, and here's my reason for setting things up this way, here's a traditional version of it one often meets, that somehow the measurement problem is that inconsistency between the unitary dynamics that's supposed to happen between measurements and the collapse rule that's supposed to happen upon measurement. Or if it's not an inconsistency, at least there's an ill-definedness of just what counts as a measurement. When are we supposed to apply this new collapse dynamics? When are we supposed to evolve the system unitarily? If you've come across the measurement problem in the sort of semi-popular literature, I suspect that's the version you're most likely to come across. This is an out-of-date way of thinking about the quantum measurement problem. For the reasons I've just been spelling out, collapse of the wave function isn't really part of the necessary formalism of quantum mechanics. We know how to go beyond it, to use it at most as a sort of convenient shorthand for something that can always be handled by just modeling the overall evolution of the system. Here's a better way to think about the quantum measurement problem, and this is what I'm going to be talking about for the rest of the lectures. How are we supposed to understand what's being said when we say of a quantum system that its state is such and such vector in Hilbert space? And I want to suggest that physics practice gives us an apparent inconsistency in how we understand the state. We go back and forth between two ways of understanding the state that seem incompatible with one another. And to say what I mean by that, let me go to somewhere where we don't have conceptual problems of this kind. Let me go to classical mechanics and remind you that in classical mechanics, we have two very different things we mean when we talk about the state of a classical system. So here's one thing we mean in classical mechanics by the state of a system. If we're working for definiteness in Hamiltonian mechanics, the state of the system is a point in the phase space of the system, position momentum pair. What does that point represent? It represents what the actual physical properties of the system are. If the state of the system is QP, what we mean by that is the actual positions of all of the particles or configurations of all the fields, whatever, are given by Q, and the conjugate momenta are given by P. And if you were to observe the system, you would, provided you did it correctly, you would find that the position of the particles was indeed Q and the momentum of the particles was indeed P. And we have a dynamics on the space of states of that kind, which modulo a minus sign that's fallen off my slide, sorry, is the familiar Hamiltonian equations of motion. And that's unmysterious. But there's a different notion of classical state, which is also fairly unmysterious. Sometimes by the state of a classical system, particularly in statistical mechanics, we mean not a point in the phase space, but a probability distribution over the phase space, representing a probability distribution over the physical properties of a system. If I say my system has state rho, I don't mean that that's a physical fact about the specific system in front of me. I mean something like a large class of similarly prepared systems would have this fraction of particles having this position, this fraction of particles having this position. Or maybe it means something like, I don't know where the particle is, but I have some partial information about it, which I represented by a probability distribution. And that notion of a classical state also has a perfectly well-defined dynamics. It's given by the Liouville equations. The rate of change of the probability distribution is its Poisson bracket with the Hamiltonian. But of course, in a certain sense, in classical mechanics, that's not the only way the probability distribution evolves. If I look at the probability distribution, and I in fact find that the particle is over here, then I update the distribution by conditionalizing on that location. And so doing physics with a probability distribution is a mixture of allowing it to evolve under Hamiltonian flow when I don't observe it, and conditionalizing on the results of my observations when I do observe it. Those two notions of classical state are largely unmysterious. There are some interesting puzzles and paradoxes in statistical mechanics into just what the probabilities are that we're talking about. You saw I slightly hedged there as to how to think about them. But ultimately, we basically think we understand both the phase-space point notion of a state and the phase-space distribution notion of a state. And we understand the way we use dynamics to evolve both of those in time. So now, how about the quantum state? Well, there's two ways to think about it. We could think that the quantum state is like the classical phase space point. It represents the physical properties of a system. Sometimes in the quantum information literature, this gets called psi ontic, psi for the usual use of psi to represent the quantum state, ontic off the philosopher's word ontology, what there is. If we read the quantum state that way, we run into trouble, famous trouble, at the macroscopic level. We run into the fact that the unitary dynamic seems to predict that we can get systems in macroscopic superpositions, that measurement processes can end up with the measurement device in a superposition of reading one thing or another thing. If we borrow Schrodinger's famous bloody example, then if we if the method of carrying out our experiment is if the system is in state spin up, we kill the cat. And if the system is in spin down, we don't kill the cat. Then if we prepare the system in a superposition, alpha spin down plus beta spin up and make the measurement, then after the measurement, the cat is in the state alpha live cat plus beta dead cat. That's just Schrodinger dynamics. That's just unitary evolution. But if we think the quantum state represents physical properties, then that seems to represent a cat that's alive and dead at the same time. Well, firstly, that doesn't seem to make sense of the Born rule. It seems that the cat evolved deterministically into this weird indefinite state rather than stochastically into either a live state or a dead state. So it's seriously mysterious at the macroscopic level how to think about quantum mechanics if we think the quantum state represents the physical properties the system's in. And that might lead you to say, well, that's already a reason why we find out we need to talk about things like collapsing the wave function, because of course, if the wave function collapses on measurement, we'd end up with only live cat or dead cat, and we put the probabilities back in. So yes, the picture of the quantum state as like the classical phase-space point has a problem with macroscopic superpositions. It has the classic Schrodinger's cat problem. We wouldn't get the Schrodinger cat problem if we said that the quantum state was like the classical phase-space distribution, that it was representing probabilities of some kind rather than representing physical properties. And again, in the quantum foundations literature, you sometimes see this called psi-epistemic, epistemic for the philosopher's word epistemology, meaning knowledge, information. And so the idea there is that the quantum state might represent our partial information about the state system's physical state rather than the physical state directly. If that was true, then macroscopic superpositions wouldn't be a problem. Alpha live cat plus beta dead cat wouldn't describe some weird indefinite cat. It would just describe a cat that was either alive or dead, and we didn't know which. And the Born rule, the probability rule, wouldn't be mysterious either. The whole nature of the state would be to represent the probabilities. So, of course, that's what we find on repeated measurements. But life's not that simple. The problem with the psi-epistemic probability reading of the quantum state is that it doesn't make sense of interference. And just to remind you of things you've known a long time in quantum mechanics, the core paradox of quantum mechanics comes from the fact that we can interfere different ways things can go. I can tune my interferometer in such a way that even when I send through photons one at a time, every single photon arrives at the top detector and no photons arrive at the left detector. If that's the case, then I can insert something into the left-hand beam so that all the photons end up at the right detector just by changing the path length a bit. I can insert something into the right-hand beam so that all the photons reach the right-hand detector. In other words, I can deterministically change the outcome by messing with the left-hand beam, and I can deterministically change the outcome by messing with the right-hand beam. And that's incompatible with the idea that the particle is in fact in one beam or another, and I don't know which. So, any state of the form superposition of photon goes the left beam plus photon goes the right beam can't straightforwardly be understood as just expressing my ignorance of which beam the photon is in, on pain of making no sense of interference. What we do in physics in practice is we kind of shift back and forth between the two. When we're doing interference, when we're doing quantum experiments, we treat the quantum state representationally, like we treat a classical phase-space point. When we need to think about measurements or the macroscopic or observation, we shift to talking about the quantum state probabilistically as not telling us determinately what's going on, but telling us some partial information about what's going on. And the way I would think about the measurement problem is how do we coherently, consistently understand quantum mechanics? How do we make sense of what's going on in quantum mechanics in a way which lets us consistently say what the quantum state is doing, what kind of role it plays in our theory? Is it playing a representational role? Is it playing some more informational role? Is it somehow parts of both? But if so, how exactly do we understand that? How do we avoid this sort of inconsistent back and forth between different ways of understanding it. So that's the measurement problem. How do we make sense of quantum mechanics? And specifically, how do we interpret the quantum state? How do we do it in a way that avoids both the problem of interference, which seems a crucial problem for a probabilistic reading of quantum mechanics, and the problem of Schrödinger's cat, which seems a crucial problem for a physical representational reading of quantum mechanics? I might just pause there and see if there are any questions so far.
There is someone who commented before, how does the system know that the state is prepared?
Good question. I mean, there's a sense in which preparation is a fairly arbitrary line that we put down in a physical process. I mean, as far as the lab's concerned, there's no bell that rings magically to say the system is now prepared and now we're doing quantum mechanics on it. We can sort of somewhat arbitrarily say, okay, everything up to this point is preparation. Now everything from here on is dynamical evolution, and now everything from here on is measurement. But the universe doesn't really care where we put these lines. This is another reason, actually, to be skeptical of the fact that claps can be playing a role in the way we formulate the theory, because it's really a matter of convenience and interpretation when we say the preparation has finished and the physics, the experiment has started. Does that help? That was a question in the chat, I guess. So if the person who asked it wants to follow up, please do. Otherwise, I'll carry on.
Oh, I have a question about
Sure.
why is it that the measurement problem appears in quantum mechanics, but not in classical mechanics? Especially, could you please explain again why is it that the interference is a problem for the psiontic interpretation? Sorry,
Yeah, I mean,
for the psi.
yeah.
I forgot the
So
name.
there's no the short answer is there's no interference in classical mechanics. So in classical mechanics, we have a dynamics for the classical phase-space distribution, the Liouville equation, but we have an underlying microscopic dynamics in the form of the Hamilton equation for how the individual phase-space points evolve. And then the Liouville equation could simply be telling us how our partial knowledge of the classical system evolves under that flow. And the probabilities there behave as probabilities. They can't cancel out or reinforce. In quantum mechanics, we've got an evolution equation directly for the quantum state. But if we're supposed to be thinking of the quantum state like the phase-space distribution, we don't straightforwardly have anything that looks like the equivalent of the classical phase-space points. And so we don't have any way of reading the quantum dynamics as just something like Liouville's equation. And the presence of interference is a reason to be skeptical we can have that. I'll say a bit more about that in a moment, in fact.
Okay, thanks.
In fact, I'll move on to this point because actually this is going to come up fairly directly to exactly what the question just covered. So let's talk about how we might solve this problem. And what I'm going to mean by solve this problem is basically how do we get this consistent understanding of the quantum state? And I'm going to basically consider four things we might try. One thing we could try is we could say, well, maybe this is an unsolvable problem for quantum mechanics. Let's replace quantum mechanics with a new theory. To which I think my main result is, well, you first. Quantum mechanics is extremely successful, extremely complicated. Quantum field theory is more complicated. We have constructed what I would think of as toy models that might supplement or modify quantum mechanics to avoid the problem of macroscopic superpositions without getting into trouble with the problem of interference. But those models are at most valid in the non-relativistic domain. They don't apply to quantum field theory. So I'm actually going to put aside entirely for the moment attempts to say we should replace quantum mechanics. I'm going to say, how do we understand quantum mechanics itself? How do we solve the measurement problem within quantum mechanics? The second thing we might try, and this relates to the question we just had, is, well, maybe notwithstanding interference, there's some consistent way to understand quantum mechanics the same way we understand classical statistical mechanics. Third possibility is maybe we can understand quantum mechanics as always a partial description of something relative to some external context that's not quantum. I'll say more about what I mean there, but if you think about the whole idea that Niels Bohr had, that somehow there has to be a classical description wrapped around quantum mechanics, or if you think about the idea that measurement might be an external primitive, or that observers have a special role to play in quantum mechanics, all of these ideas, which don't really have analogues in classical mechanics, might point to different ways of understanding quantum mechanics. And fourth, and this is my own preferred approach to this, we should just use quantum mechanics itself to model measurement, model the environment, model all the macroscopic processes in detail, not just in schematic things like alpha live cat plus beta dead cat, but in detail, and see if somehow we can suppose that quantum mechanics really is representing the physical properties of the world, but nonetheless kind of looks emergently probabilistic when we consider what macroscopic dynamics are like. And I'll talk briefly about each of those routes 2, 3, and 4 in the rest of the lecture. So number 2 there is very much the suggestion that just came up in the discussion. And the general name for that approach gets called the, I'll put this in parentheses, epistemic hidden variables approach. For people who might know some of this literature, I say epistemic hidden variables approaches because there are other approaches to quantum mechanics which keep the quantum wave function, the quantum state around, but add additional variables as well. Something like the de Broglie-Bohm theory has this character. But I'm not thinking of that sort of approach here. I'm thinking, if we think of quantum mechanics as something like classical statistical mechanics, we need to find the theory which stands to quantum mechanics as classical mechanics stands to classical statistical mechanics. So you might call this a sub-quantum theory, a theory of the sub-quantum properties, such that the quantum state can be interpreted somehow as a probability distribution over those sub-quantum properties. And we found in 100 years of looking at this that it is virtually impossible to do this. We've proved a large class of no-go theorems that seem to say it's practically impossible to have any non-pathological theory that could be the equivalent of classical mechanics, so that we could think of quantum mechanics as the equivalent of classical statistical mechanics. The earliest of those theorems was proved by von Neumann. It has a number of substantial flaws. Much more has been learnt since then. Probably the state of the art, although it's slightly too complicated for me to go into in the time I have, is the Prusi-Barrett-Rudolph theorem, or the PBR theorem, proved about a decade ago. I'm going to just use as an illustration of the sort of problems, sort of intermediate case, the Koch-and-Specker theorem, in the form that David Merman worked out in the early 80s, just as a sort of flavor of the kind of difficulties, and just also to build your intuitions as to what we mean by an interpretation of quantum mechanics along these lines. So I want to consider a system of 2 spin half particles, 2 qubits if you're quantum information inclined. As usual, I can have spin x, y, z for these particles. The idea of at least one large class of hidden variable theories of this sort is that when I measure spin, what I find is the actual genuinely possessed value of the spin. In other words, the particle actually really is either spin up or down in the x direction. Really, it's either spin up or down in the y direction. Really, it's either spin up or down in the z direction. In each case, we don't know which. When we measure it, we find out. Presumably, when we make the measurement, we disturb it as well, so that we shake up the other values it might have. But in any case, measurement is just revealing what the possessed value of the quantity is. And the Koch-and-Specker theorem basically tells us that that can't be done. I'll say a bit in a moment about how this links to the original Koch-and-Specker, but here's a sort of beautifully simple illustration of that everyone should know. So I want to consider this sort of grid of 9 possible measurements I may make on the system. So for instance, the top left quantity says, well, what is the, I could be measuring spin for the first particle in the x direction and not bothering to measure anything on the in the for the second particle, and the result of that, there'll be some result of that joint measurement. I'll measure both of them and take the product of them. So I'll definitely get 1 for the second measurement. I'll get +1 or -1 for the first measurement. By measuring both, I'll get a joint answer. So then here are 8 more joint measurements I might make of the system. So the nice thing about this diagram is that along the rows in each case, the first element commutes with the second element. In other words, we could multiply them, we could measure them simultaneously, and their product is the third measurement. So if that's right, and the system really had values of these quantities, then the value of the third measurement on each on the first row should be the product of the first 2 measurements. So if the first measurement gets result A, if the actual value of the quantity for the first measurement is A, and the actual value of the quantity for the second measurement is B, the actual value for the third one should be AB. And the same is true on the second row. So the if the result of the first measurement is C, or if the actual value that the first measurement measures is C, and the actual value the second measurement measures is D, then their product is CD. And now if you look at the first 2 columns, you can see also that the first 2 elements in the first column commute, and their product is the third element, and likewise the second column. So the result in the bottom left corner had better be AC, and the result in the bottom middle should be BD. But now we have a problem as to what's going on in the bottom right corner, because the product of the first 2 elements on the last row is, and they also commute, I should say, is plus the third element on the last row. So that should say that the entry in the bottom right should be plus ACBD. But also in the last column, the first 2 elements commute, but their product is minus the third element. So the bottom right corner on that logic should be minus ABCD. In other words, the result of the possessed value for the bottom right corner has to be ABCD and minus ABCD. And A and B and C and D must each themselves be +1 or -1, plus half or minus half, actually, if you normalize it the usual way. But in any case, not 0. And that's clearly mathematically impossible. So this is just an illustration of the kind of class of no-go theorems we have for hidden variable theories of this kind. All no-go theorems have assumptions. It's always possible that there's some ingenious loophole in the various results that are known that says maybe there really could be this epistemic hidden variable theory. But we know by now that the theory would have to be pathologically strange in many respects. And most people, certainly including myself, regard the prospects of finding a theory of that kind as extremely dim. That takes us to the third possibility, but I think since we've been going for about an hour, this is probably a good time to take a break. So if that works for you, Daniel, why don't we stop now for... So just to recap where we came in, I said that the measurement problem, as I was cashing it out, was how do we understand the quantum state and therefore the content of quantum mechanics? Do we understand the quantum state probabilistically? Do we understand it as describing physical features of a system or something else? I briefly passed over the idea that we might change quantum mechanics in response to the issue, and I said I thought it was a long shot. I discussed the fact that if we want to think about quantum mechanics just the way we think about classical statistical mechanics runs into a large class of no-go theorems that suggest it will be extremely difficult to build any such theory. But there's another way, other than the classical statistical mechanics way, we might make sense of the quantum state as nonetheless saying probabilities, which is that those probabilities are somehow relative to some experimental context that's external to quantum mechanics itself. So we don't think that the quantum state encodes the actual probabilities that the system has some agent invariant properties. We have some idea that the quantum state encodes facts about what agents expect to encounter, or facts that are described classically, or facts that are relative to the experiment carried out. This idea is as old as quantum mechanics itself. Niels Bohr talked this way a lot. So people have had various ideas how you might do this. You might say, okay, maybe we have to give an external classical description of measurement, and then quantum mechanics is relative to that classical description. People have sometimes said, this is common in quantum information, measurement should be regarded as a primitive process. A measurement is not something, it's not the job of quantum mechanics to analyze why something's a measurement. It's just a basic posit that something is a measurement. These have in common the idea that we're dropping the idea that measurements and experiments are things that are themselves modelable quantum mechanically. And there's a lot that could be said about that. In the break, somebody was asking about realism, and a philosopher's objection to this kind of approach might be that if we just think quantum mechanics is relative to some primitive notion of external measurement, we've given up on any idea to understand the world as it is, rather than as it is relative to us as experimenters. But, you know, maybe we're relaxed about that. A more serious problem, I think, is that the actual practice of physics requires us to model measurement and model it quantum mechanically. I mean, back when Niels Bohr was writing, back in the heyday of the Copenhagen interpretation, when quantum mechanics was in its infancy, it made sense to say, well, maybe we always need a classical description of experiments, and we can use classical mechanics to describe experiments. And if you think about the famous debate between Bohr and Einstein, a lot of that turns on these detailed classical explanations of how a measurement works. But modern physics has moved on a long way from that. And in many cases in modern physics, we actually need a detailed quantum mechanical analysis of the measurement device itself. Since this is a quantum field theory course, I thought I might give you a quantum field theory example. It's not super well known. So let's suppose we're thinking about measuring position of a particle. Now, this is a classic kind of thing that was discussed in the early days of quantum mechanics. And for many purposes, it suffices just to hand wave what we mean by a position measurement, just to use our classical notion of what position is. But things get interesting in a relativistic theory when we try to say what position is in any detail. So if you think about non-relativistic quantum mechanics, quick revision for you, position observations are defined by the eigenstates of the position operator. If the eigenstates, the position operator can be expressed in terms of the momentum operator, they're Fourier transforms of momentum eigenstates. All of that's perfectly well behaved. This quantum state X forms a basis. It's an improper basis, but it forms a basis. These quantum states are defined a self-adjoint operator in a perfectly satisfactory kind of way. There's a typo on the second line of this slide, apologies. Ask yourself how you might define position eigenstates in relativistic quantum mechanics. Usually in relativistic quantum mechanics, we tend to make momentum measurements. We tend to apply the Born rule on the momentum basis. But suppose we did try to make a position measurement in relativistic quantum mechanics. Well, how would we define the position eigenstates? And therefore, how would we define the position operator? Now, there are two options you might choose. The integral dk cubed, relativistically, again, you're probably all familiar with this, is not relativistically invariant. To make it relativistically invariant, I need to put a factor 1 over root k squared plus m squared underneath the dk cubed term. I put it outside the integral sign, just a typo preparing the slides, sorry. So that definition of a position eigenstate would say I'll take the covariant Fourier transform of the momentum eigenstates. That defines a covariant eigenstate, a set of position eigenstates, but they have the property that they're not orthogonal to one another. This what I wrote on the line below is a momentum statement. It should read inner product of x and y is not equal to the delta function of x minus y. If you think about position eigenstates, the whole idea is if the particle is definitely here, it's definitely not there. These have to be eigenstates of some observable. They need to be orthogonal. Covariantly defined position eigenstates aren't orthogonal. Alternately, we could say we'll just use the non-covariant definition of a position eigenstate. We'll just say, just like in non-relativistic quantum mechanics, the position eigenstates are the ordinary Fourier transforms of momentum eigenstates. This is called the Newton-Wigner position observable. It does obey the orthogonality property. It is the case that if a particle is here according to this definition, it's definitely not there. But that definition is not Lorentz invariant. If I take a state that is localized according to this definition in one reference frame, it will be delocalized if I Lorentz boost to a different reference frame. So there's no completely satisfactory understanding of what a position observable could be in relativistic quantum theory. Now, we've learned a lot about quantum field theory. We know that particles are not fundamental in modern quantum field theory. Particles are certain kind of excitations of quantum fields. The quantum field theory has a pretty well-behaved notion of locality. So there's no deep mystery here. But what it does tell us is that if you had a machine that purported to measure the position of a relativistic particle, then exactly what it was measuring couldn't just be read off from our classical intuitions. It would require a quite detailed quantum mechanical analysis of how the measurement process is working. In other words, saying we'll treat the measurement process as primitive or the measurement process as classical wouldn't be an option. And issues like this are fairly ubiquitous. The general way we do physics does not treat measurement devices as primitive. It does not treat the measurement context as external. It often doesn't treat us as having anything as simple as a lab. If you think about using quantum mechanics in modern inflationary theory, we're describing how structure forms in the early universe as a whole. We don't prepare the early universe in a certain state and then externally measure it. The external universe just does its thing, and we infer forward as to what that says about the microwave background radiation or distribution of galaxies. Either way, we don't seem to be doing physics in a context where we have external measurements, classical processes. So there's a lot more to say in defense of an exploration of these kind of external observer, external classical description, primitive measurement approach. And it's been very productive as a kind of way of thinking in the very stylized context of quantum information. But I think there are quite severe problems if we try to take that approach to quantum mechanics and apply it to quantum field theory and modern quantum cosmology and just the general shape of detailed applications of quantum theory in the modern precision measurement era. This is just a slide to summarize this. So that then takes us to the last possibility. What about if we want to spend a bit more time looking in more detail at just how we might quantum mechanically measure the process whereby a macroscopic superposition might be prepared? Where I came in was, well, the system couldn't possibly be in a state like alpha live cat plus beta dead cat, because how does that compatible with the Born rule? Well, let's look more carefully at the physics of how those macroscopic systems come about. And the general jargon term here and the sort of profusion of work that's come out of thinking about that question comes under the rubric of environment-induced decoherence. And what I mean by environment-induced decoherence is it's the process that happens when my system is being constantly and repeatedly measured with respect to some fixed basis. So if you think about Schrödinger's cat, the cat is not an isolated system. The cat is surrounded by the air in its box. The cat is interacting with the light coming into the room the cat's in. The cat is even interacting with gravitational radiation. The interactions can be very small, but there are very many of them. A given photon will scatter in one direction if the cat's alive and a different direction if the cat is dead. And you can think about that measurement as the classic form of what a quantum measurement is. It's a system, remember the definition earlier, where the post-measurement state of the system doing the measuring is correlated with the pre-measurement state of the system being measured. So if the photon goes one way if the cat's alive and another way if the cat's dead, then the photon is measuring whether the cat is alive or dead. And even if we ignore the external environment to the cat, then the cat has an enormous number of internal degrees of freedom that we're averaging over when we just describe the cat in coarse-grained terms as alive or dead. And, you know, where the way some particular phonon in the vibrational modes of the cat's tail will behave will depend whether the cat's alive or dead. And so the internal degrees of freedom of the cat are also constantly and repeatedly measuring the cat. And we model all that unitarily. We model that the same way we were modeling those stylized repeated measurements that I discussed earlier in the course. We treat the cat plus its environment, or for a more realistic model, some large particle plus its environment, as one big unitary process. And we study how the system itself evolves under that constant unitary process. And the consequence is, because of all this measurements going on, the system is constantly becoming entangled with its environment. If I try to prepare a coherent superposition of a macroscopic object that's in two places, or a cat that's alive and dead at the same time, the coherence of the superposition will be washed into the environment by the entanglement. And a helpful way to think about this, I won't go through the technical details of this just on reasons of time, but if I adopt the density operator formalism, so if I describe the quantum state of the system in isolation by a density operator, which is in general necessary because of entanglement, then the constant process of measurement with respect to this measurement basis of the environment approximately keeps the density operator of the system diagonal in that basis. And that means that interference with respect to that basis is suppressed. How do I tell if my system is in a coherent superposition of here and there, or just in an incoherent mixture of here and there? Answer, I do an interference experiment between here and there. But if the environment is constantly suppressing the cohesion between those, I won't be able to tell. I won't be able to do the interference experiments, which prevent, as a practical matter, me interpreting the quantum state probabilistically. And if I've got a large system, a macroscopic system, interacting with its microscopic environment, then this process of decoherence can extremely rapidly suppress interference while otherwise leaving the system largely alone. So my favorite example here is Jupiter. So Jupiter is macroscopic if anything is. Jupiter is interacting with a whole bunch of environments around it, but to pick a particularly ephemeral one, Jupiter is interacting with the cosmic microwave background radiation. You know, microwave photons from the early universe are constantly scattering off Jupiter. Now, if you do planetary physics, if you study celestial mechanics, you don't spend a lot of time worrying about the dissipation, the dissipative loss of Jupiter's momentum as a consequence of scattering off CMB photons. Technically, it's happening, but it's so small that you can utterly neglect it. We totally don't care about the effects of microwave background photons on Jupiter. But the reason we don't care about that is because we start by assuming Jupiter is in an approximately localized state. That if I did a quantum mechanical description of Jupiter, its center of mass is in a very narrow wave packet. Suppose instead, somehow, these super aliens, high technology, we prepared Jupiter in a superposition of two different places, like superposition of where one place it could be and a million miles in the other direction. Well, extremely quickly, that will be decohered. One microwave photon will do it. If I've got a superposition of Jupiter here and Jupiter there, and I'm considering one photon that's on a trajectory towards here, well, the system will evolve into a superposition of Jupiter here, photon deflected, plus Jupiter there, photon undisturbed. And now the coherence is gone. If you did a density operator of this, you'd find that the state of Jupiter is diagonal in the here-there basis, in the position basis more carefully. And so even leaving aside the other technical difficulties, it would be impossible in principle to tell that the quantum state of Jupiter was a superposition of here and there, unless you can reach out and grab that microwave photon and include it in the experiment. And there's millions more coming in every second. So Jupiter is being very rapidly and repeatedly measured with respect to its position. And because of that, any quantum mechanical aspects of how Jupiter is moving are very, very rapidly suppressed, even though otherwise its dynamical evolution is completely untouched. I'll just mention for completeness a slightly less hand-waving and more rigorous model of how we might do it. So the general workhorse for exploring environment-induced decoherence is the Caldera-Leggett model. What I imagine is I've got a single massive particle. It could be Jupiter in my previous example. It could more realistically be like a dust grain or something. That particle's moving freely, or it's moving in a harmonic potential. I've also got a very large number of environment systems. And for simplicity, we normally treat, in this model, we treat this as an oscillator bath. So my environment systems are uncoupled harmonic oscillators. That's not a bad model for, say, if the bath is black body radiation, or if the bath is the black body phonons in a warm crystal or something. And I assume a linear coupling between the particle and the oscillator bath. You can actually solve this problem exactly, but it's more helpful to take a few approximations, to assume a separation of scales where the dynamics of the particle is very, very slow compared to the dynamics of the oscillator bath. And then you find an evolution equation for the density operator describing the particle that's the sum of a unitary part, that's the first term, and two other parts which jointly describe decoherence and dissipation. So decoherence, the suppression of coherent superpositions with respect to, in this case, roughly position. Dissipation, the actual slowing down of the particle from just bulk interaction with the environment. And what you find is, again, for realistic choices of parameters, for something like a macroscopic superposition, the toy version of Schrodinger's cat or something, you find that the decoherence term is extremely fast, even while the dissipation term can be neglected, which is to say that the density operator collapses extremely quickly onto a diagonal density operator, which then evolves in a way that otherwise doesn't care much about what the oscillator bath's doing. For the sake of intellectual honesty, I should say it does care in the sense that there's a renormalization term going on here. Again, if you're all doing a high-energy physics course, you've spent a lot of time, I'm sure, thinking about renormalization. As you know, renormalization contributions get absorbed into the effective unitary dynamics, and you can see that's what's going on here. The Hamiltonian for the unitary part of the particle's evolution has this renormalization term, half m omega squared x squared. So why do we care about this? What is all this delivering if we're thinking about just unitary quantum mechanics as it's applied to modeling macroscopic superpositions? Well, it's delivering a basis for the system, usually a basis of localized wave packets, such that the density operator of the system is approximately diagonalized with respect to that basis, not instantly, but on timescales that are short compared to the dynamical evolution timescales. That is, compared to the timescale on which the system itself evolves. And we're also getting, and this is crucial, an approximately autonomous dynamics, that is a self-contained dynamics for the system's density operator. In other words, we can actually write equations of motion for the density operator and solve it. It makes sense to ask, what's the density operator's dynamics? What's the dynamics of the system? The system's dynamics are not unitary, but they're still dynamics. They're still well defined. Why do we care about it delivering those two things? Well, given decoherence, at a formal mathematical level, the spontaneous evolution of the system is stochastic. Because interference is being suppressed very rapidly, with respect to this decoherence basis, the system's own self-contained dynamics is just the dynamics of a probability distribution over the decoherence basis. That might be deterministic, it might be stochastic. The system, a quantum version of Brownian motion is the classic example of stochastic dynamics. The Brownian particle is very rapidly decohered by the bath it's in, and it then random walks around. That's a case where both the decoherence and the dissipation are large. And not only is the spontaneous evolution of the system, formally speaking, stochastic and not quantum mechanical, any external intervention will fail to induce interference events. In other words, if we are trying to do an experiment to coherently superpose states in the decoherence basis, we'll fail, unless we can do it so fast that it happens before decoherence kicks in. And normally the decoherence timescales for macroscopic systems are extremely fast, such that no realistic intervention can be done. Now, remember, go back to the different ways of understanding the quantum state I was discussing. The problem with understanding the quantum state probabilistically is interference. So what this is telling us is, as long as we're working at the macroscopic level, as long as the system we are studying is decohered with respect to a certain basis, then nothing will go wrong if we take an approximate probabilistic reading of the quantum state with respect to that basis. If we were to stop treating the system as a highly entangled superposition and just treat it as a probabilistic mixture, nothing will go wrong when we do it. In other words, the predictions we make using the Born rule eventually will come out the same. Yeah, go ahead. I thought I heard somebody had a question. Perhaps I misheard. Okay, let me carry on. And this is basically the core starting point of the Everett interpretation, as it's currently understood. Unitary Schrödinger dynamics brings about macroscopic superpositions that formally look like probability distributions, evolving deterministically or stochastically. At the microscopic level, we absolutely can't think of quantum states as probability distributions because of interference. But at the macroscopic level, formally speaking, there's no barrier to doing so. So we can't systematically think of the quantum state as a probability distribution. And even at the macroscopic level, given a sufficiently large level of control, nothing in the laws of physics prevents even arbitrarily large superpositions being reinterfered. So if actually we threw away all but one term in a superposition, even at the macroscopic level, we could get the physics wrong if some future process does carry out some implausibly complicated reinterference. And thought experiments of this kind have been quite important in black hole thermodynamics and in understanding the information loss paradox in Hawking radiation, I should say. So what the Everett interpretation says, going back to our how do we understand the quantum state, is it says fundamentally we understand the quantum state representationally, which means that fundamentally speaking, even when we have a macroscopic superposition, we can't say it's literally a probability. All the terms are still present in the superposition, hence the many worlds language. There's a dead cat term in the superposition, but there's also a live cat term in the superposition. And even if I observe the cat to be dead, the live cat branch of the superposition is still there and still has a version of me who sees alive, and that branch is not unphysical, even if in practice it can't interfere with me, so I can't see it. That's what's going on fundamentally, but at the emergent, the approximate level, things look probabilistic. They look probabilistic, at least in the formal sense, that the probability calculus is obeyed, that the dynamics has the properties of a probabilistic system. Now, somebody raised earlier, is it sufficient to say that the the macroscopic dynamics has the formal structure of probability in order to justify the Born rule? Or do we need more? Put another way, if fundamentally the world is a macroscopic superposition of a state where the cat is alive and a state where the cat is dead. And if the mod squared amplitude of the live cat branch behaves dynamically the way a probability should behave, and the mod squared amplitude of the dead cat branch likewise, is that enough to say we can understand it as a probability? Or do we want to say, no, it still doesn't make sense to think about probability in a situation where all of the outcomes are simultaneously present in the superposition? And I'm not going to talk very much about that here, although I'm happy to talk in the questions. And the main reason I'm not is because I think as a philosophy problem, it's pretty interesting, but as a physics problem, it's not terribly crucial. In general, in physics, what we need for some part of the mathematical formalism to be interpreted a certain way is that it has the right formal properties to be interpreted that kind of way. We don't ask, in say, general relativity, once we know that the space-time metric has the right formal properties to describe space and time intervals, and that those formal properties are appropriately preserved in the dynamical process of measuring them, we don't normally say there's a further question to ask about whether they're really really lengths and really times. So likewise, as a matter of physics practice, we wouldn't normally think we have to ask, why is something that has the right formal properties to be a probability really something we can treat as a probability in our experimental practice? Furthermore, if we do ask the question, why is it probability, then we have to answer the philosophical problem of what probability is anyway, even outside the context of quantum mechanics. Now, there are things you can say there. Maybe probability is some measure of relative frequency. Or maybe probability is simply a measure of our preferences in carrying out experiments and indeed maybe making bets, and maybe probability quantifies things like our level of confidence in scientific hypotheses. Those are both defensible readings of probability in philosophy of probability. And on either of those readings of probability, then there are, to be sure, controversial arguments and mathematical results inside unitary quantum mechanics, that is, inside the Everett interpretation, that those probabilities can be understood. Those arguments do tell us that the mod squared amplitudes are indeed probabilities. But there's a great deal more to say about that, more than I have space in these lectures to develop. So let's just park at the moment the fact that there are deep philosophical questions about what probability can mean in a theory where fundamentally we understand the quantum state as representing what the theory is doing, and we get the probabilities out emergently, approximately at the macrophysical level through the process of decoherence. Okay, so I've come mostly to the end of what I want to talk about here. Let me sum up where we are. Ways to solve the measurement problem. Firstly, we could replace quantum mechanics as a new theory. That's been a valuable, interesting, useful research program in the 20th and 21st century. It's provided a lot of insight into what's necessary in the quantum formalism, which bits can be changed without effect. It's also been very much a parameter framework for how we might test quantum mechanics, how we might test the superposition principle, how we might look at how experimental evidence bears on quantum mechanics. I'll give a quick example of this. The way you might want to test, one way you might want to modify quantum mechanics is you might say, okay, the formalism doesn't have a collapse mechanism, but a collapse mechanism would remove Schrodinger's cat. So maybe we should add a collapse mechanism explicitly to the physics. And there have been proposals as to how to do that. How would you test a theory that says wave function collapse really happens? The answer is you would have to prepare some superposition where it was protected from decoherence and could still interfere, but somehow was otherwise large enough that your mechanism for collapse kicked in. How would you do that? Well, you need some very large, relatively large object that you could keep very well insulated from its environment, and then do complicated, delicate interference experiments on it. Foundations of physics doesn't have the budget to build things like that. Gravity wave astronomy does have the budget to build things like that. And although the LIGO Observatory's primary function is, of course, to observe gravitational radiation, it turns out it's also a pretty stringent test of the superposition principle in quantum mechanics, and a quite large class of theories where we change quantum mechanics by introducing a collapse have been ruled out or very heavily constrained by data from LIGO. Like everything we see from LIGO is compatible with quantum mechanics, with unitarity, with the universality of the superposition principle. So my point is that these attempts to replace quantum mechanics have, in the large, been good science, but it's enormously demanding, and although you never know, it doesn't look to most people as if the prospects of doing this are particularly sunny. We could, as I discussed previously, try to find a consistent way to understand quantum mechanics like classical statistical mechanics. We've learned a huge amount doing that, about the structure of quantum mechanics, but most from the von Neumann's early results to non-contextuality, to Gleason's theorem, to the Kochen-Specker theorem, to the PBR theorem, to the Leggett-Garg inequality. But most of what we've learned has been negative. Mostly we've learned things of the effect that if there was a way to understand classic quantum mechanics like classical statistical mechanics, it would have to have the following enormous class of pathologies. So I would say those approaches are almost completely ruled out. We could try to understand quantum mechanics as describing physics relative to some agent or measurement context or classical context, indescribable within quantum mechanics itself. Again, in quantum information, that approach has been a pretty valuable perspective. A whole bunch of theorems and formal results have been proved by exploring things in that way. We've learned a lot about what components of quantum mechanics really do the work in quantum interference experiments like teleportation or fast computation. But if we want to apply this in concrete applications where it actually physically matters how measurement works, there are severe difficulties. And then that leaves us with Everett, by which I simply mean treat quantum mechanics as self-contained, treat probabilities and classicality as dynamically emergent from an underlying unitary dynamics applied to a quantum state, which fundamentally has to be thought about as physical, and therefore has to be taken that way, even in the context of macroscopic superpositions. There's a fifth approach, often comes up particularly in high energy contexts. Couldn't we just shut up and calculate? And there's a lot to be said for that. But one of the things I'd like you to take home from this lecture is shutting up and calculating is not an alternative to how we want to think, to model and handle the approach to measurement. Shutting up and calculating still requires us to shut up and calculate within some way of treating measurement. Nearly always, when people say they want to shut up and calculate, they mean, let's just do everything unitarily, let's just calculate how the measurement process works. And in that sense, the shut up and calculate interpretation is really just the Everett interpretation, just without an interest in getting philosophically sidetracked by literal discussion of many worlds or of philosophical questions of probability. I often say that when people say let's shut up and calculate, what they really mean is let's shut up and calculate in the Everett interpretation. Okay, there's enormously more I could say, but that's all I think it's good for me to say now. We've got about 15 minutes left if there are further questions. I'll leave up, and these are in the slides, a few references that are valuable, potentially valuable. The first of the two papers by me there is really just a way of stating what the measurement problem is in the way I've cashed it out in the first third of this lecture. The second of the two references by me is an encyclopedia article, which I put up not so much for its own use, though I hope it's of some use, but mainly because it'll work as a source of references for most of the things I've been saying throughout the course of these lectures. And there's a Sidney Coleman classic lecture that he gave a number of years ago, but which relatively recently was put up on the archive, which, if you like, you could roughly define as shut up and calculate in the Everett interpretation, and is well worth your time if you haven't looked at it. Coleman, of course, is somebody very much in the high energy physics, particle physics tradition, but who also thought quite deeply about the interpretation of quantum mechanics. Great. I will stop there, I think. Thank you very much.